We looked at the relationship between the rate of a reaction and the concentration of a reactant last week, right? We looked at how the rate of the reaction slows down as the concentration decreases, but that relationship can be different for different types of reaction. What we're going to look at today is the integrated rate law, and this gives us the relationship between concentration and time. And this is much more useful because this allows us to predict, okay, in 5 minutes, what's the concentration going to be? Or how long is it going to take for this much stuff to react? And the integrated rate law also will depend on the order of reaction. So instead of starting with 0, we're starting with the first order. So if we look at a simple decomposition, where A is decomposing into some products, we learned for first order we can write the rate law like this: rate equals the rate constant times the concentration to the first power. We also learned on the first day that we can define the rate of a reaction in terms of the change in concentration over the change in time for any given reactant or product. Because this is the reactant, it has a negative in front of it. And if we were writing 1 over the coefficient, it would be 1 over 1, so we didn't bother writing that. So that's last week. What we're going to do now is since both of these are equal to the rate, we're going to set them equal to each other. And this is known as a differential rate law. So that's all nice, but we want to get to the integrated rate law. So after integration, the magic of calculus, we get this integrated rate law. If you've taken calculus, if you like calculus, you could integrate that yourself and hopefully, we come up with the same answer. You don't need to know any calculus in this class. I pressed delete on that before you were born. I remember the general purpose of calculus. I understand its value. I don't need to do it at all.
Even before I was born?
Even before you were born, yeah. Yeah, back in the 80s. That was a long time ago. Yes, I'm old. So we can write this equation in 2 different ways. This is just rearranging it. This is a linear form. And so if you remember from math class, the equation for a line is y is equal to mx plus b. So we can graph this. Here we have the natural log of A at time t, concentration of A at any given time, is equal to -1 times the rate constant times whatever that time is in seconds, plus the natural log of the original concentration of A. And if we graph natural log of A at time t versus time, we get a straight line. The y-intercept here tells us what the initial concentration was, and the slope is equal to -k. The slope is negative, the rate constant is positive, right? So we multiply by -1. Any questions? If you're concerned about, do I have to memorize these equations? If you look at the last page of your lab manual, I gave you a copy of the information sheet that I will provide you for each exam. And these equations are on that list. They are not labeled, but I did put them in order, 0, 1, 2, because I'm not that mean, but they're there. So you don't have to work on memorizing these. Okay, so how could we use this equation? Here we have the decomposition of SO2Cl2, and we're monitoring that concentration at a fixed temperature as a function of time, meaning what they did here is every 100 seconds, they measured the concentration of that, and they put all the numbers in a table. And we are supposed to show that the reaction is first order and determine the rate constant. When we determined reaction order last week, we were looking at the rate of the reaction and the concentration. Here we don't have the rate of the reaction. So we're going to use the integrated rate law and graph this data. So you'll take the negative log, that's pH, the natural log of this number, and that'll be your y value, and x will be your time value. And we're going to learn in Excel, in lab, either today or on Thursday, how you can make Excel do all that math for you. We don't have to do repetitive calculations. I mean, who wants to take the natural log of all those numbers and write it down? Nobody does. The computer could do it for us. Okay, so we're going to learn how to do that. Well, we're not going to actually do this in class. Ta-da, there it is. The natural log of the concentration versus time. There are the data points. The computer can assign a best fit line and calculate the slope and the intercept and give us the equation for that line. Magic of science. When I was a student, we had to do this on paper and get out a ruler and draw the line and then do rise over run, and so old school. It was tedious, very, very tedious. So we'll graph that. And how can we determine if this is first order? Is that a straight line? Yeah, it's a straight line. Only a first order reaction will give a straight line for this graph. So because it's linear, we know it's first order. Now, this is a really beautiful set of data. The data is not always so pretty, right? How can we tell if it's a line or not? Well, there's something called the correlation coefficient, R squared, that the computer that you're using to generate this will also give to you. And R squared is equal to 1 for a perfect line. So if your data matches a line perfectly, you'll get R squared of 1. If you've got something like 0.8 or 0.5, that's not a linear thing. The computer can still draw a line, but it's not linear. So you're looking for things like 0.99 or better in your lines, okay? So here we have our first order reaction, determine the rate constant. Well, if we look at that integrated rate law, natural log of A at time t is equal to negative kt plus the natural log of A0. What does the slope correspond to? Negative kt. This is the slope for y equals mx plus b. So the slope is equal to negative k, which means that k is equal to negative slope, right? So our slope is 0.000290. Is that going to be a positive number or a negative number? It's going to be positive. A rate constant has to be positive. Just like negative time is meaningless, you can't have a negative rate constant. So this is the rate constant. And then we should always put units on things. What are the units on a first order rate constant? Pardon me? So I've got a couple of different guesses, and this is something that I do not expect you to have on the tip of your tongue, to just be able to remember. This is how I would just kind of figure it out. I would probably do this in my head, but I'm going to look at the first order rate law. The rate is always molarity per second. and the concentration is always molarity. So then what is the unit for K? Per second. So these would cancel out, we'd have a 1 over there. So this is s to the minus 1. Yeah. Molarity per second, great guess, that's for 0 order. Any questions? So let's use this graph and the best fitting line to predict the concentration of SO2, Cl2 at 1900 seconds. We've got this graph, it doesn't go up to 1900 seconds. But we can use the equation of the line to find out what y would be at 1900 seconds. So y is the natural log, and I'm calling it A because it's easier to write than SO2Cl2. So A at time t, which is 1900 seconds, is equal to this, right? So negative 0.000290 s to the minus 1 times the time, 1900 seconds. Didn't plan this out very well. Not plus. Minus, oh, let's do this just because I can. Minus 2.3. So this doesn't require really any rearranging, at least not yet. And get your calculator out, because I made several mistakes yesterday. So hopefully I won't make them again today, but if I do, I want you to catch me. 0.00029. The rate constant is positive, but in our equation it's negative kT. So it's actually, we're using this equation right here. So this is the slope, and the slope is negative k. So
In the equation, the actual one, there's no negative. Yeah, there's negative in front of the k.
right. So here k is a positive number, and that's the negative in front of the k.
And before we read rate constant as positive number.
But it is a positive number.
Okay.
In the equation, it's multiplied by negative 1. Okay? And that's something that I see at all levels in most of my students. Negative k, somehow we think that's supposed to be a negative number because it's got a negative in front of it. Well, that just means minus 1 times whatever that number was. Okay? But thank you for asking, because I'm sure other people were a little confused about that as well. And then minus 2.3. So I'm getting negative 2.851. We care about sig figs, but we're not going to go nuts about them. So if we look at the numbers that we've been given, 1900 seconds, that's one of those ambiguous ones. And so we don't need to worry about a number like that. We're going to look at the other things, because this is most likely to the nearest second. It's kind of sloppy, but it's how real scientists do it. Okay, we wouldn't put the decimal point there. We got 3 sig figs here and 3 there, and so our answer should probably have at least 3 sig figs. So we want to keep 3. The danger where you can get into trouble is if you round things off too much. If we rounded this off to negative 3, we would get a very different answer. So keep a couple extra digits. That's what I'm trying to say. Okay, how do we get rid of this natural logarithm?
Professor?
Yeah.
Do you think there's a line in front of the 2.3 where there is no line there? In front of the ln of the 2.3.
Well, it's negative 2.3.
Yeah. It's like, so it is not the rule that is Ln of the concentration?
This is the ln of the concentration.
Oh, okay.
Okay, so this is, I'm really glad you're asking about this because I think a lot of students really struggle with this, and it's really important to see what's going on here because we're doing all of this substituting. So this is y equals mx plus b. So negative k is the same as the slope. We take the slope and we change the sign to get k, or to get the slope, we take k and change the sign. Natural log of a is equal to y. Natural log of a0 is equal to b. And t is equal to x. So when we get this equation for the line, we don't need to do anything to it. We can just say, well, this is t, because t is the same as x, right? And y is what's on the y-axis, and that is natural log of a. And this intercept, negative 2.3, is b. So we don't need to do natural log of that value on the graph. Does that make sense? We can just use it as it is. We don't want to make things more difficult. It is important, though, to identify this as the natural log of a and not just a. It's like, oh, we'll solve for y and that's our answer. No, we'll solve for y, and that's the natural log of our answer. Anybody have questions about that? We're going to be using graphs and equations of lines a lot. So we need to just, get it straight in our heads. Okay, so e to the natural log of x is equal to x. E to the whatever is the anti-log, anti-natural log. Ln is the natural log. So to get rid of this natural log, what we're going to do is we're going to take e to the power of each side. So e to the natural log of a is equal to e to the negative 2.851. Everybody okay with that? I'm not going to step you through all the rearrangings, but this is the first time we're dealing with natural log, and so I just want to, jog your memory about what do we do with logarithms. So this then, here, simplifies to just a. So all of this is equal to the concentration of a at time t. So on my calculator, I'm going to use that e to the box button, press that, and then I still have this number in my calculator, so I can just go up and select it, press enter, and enter again. And so I'm getting 0.05778 and then I'm thinking, how many digits should I write down? Oh, 3 plus 2. So here's my 3, and I've got 2 extras, so that's good. You want to write down the extra digits here, because later you might come back and you realize, like you're trying to put it into the computer or something, and you're like, shoot, I was supposed to have 4 sig figs. Well, if you wrote down 2 extras here, all you have to do is look at it and fix it. If you round this off, then in order to get those sig figs back, you're going to have to do at least part of the calculation over again. So that's my strategy there. What's the unit on this concentration? Molarity. So in Chem 1A, we had lengths and times and concentrations and volumes and stuff, and they were in like all different units, and we were always making you convert them, right? Well, here it's like we're going to assume that you know how to do that, and we're just going to use the units that people normally use. We're going to have volumes in milliliters. So we're going to end up using millimoles when we do some calculations. Concentration, in brackets, always moles per liter. Okay, time, always seconds. So we should report our answer as 0.0578 molar. And let's see if I got that one right. Yes, I did. This is just in scientific notation. Any questions? Let's do another example. Cyclopropane rearranges to form propene in the gas phase. The reaction is first order. That's going to be important. Let's highlight that. First order. And it has a measured rate constant. Oh, that's useful. Rate constant of 3.36 times 10 to the minus 5 s to the minus 1 at 720 Kelvin. So they're giving us 720 Kelvin. Are we going to need to use the temperature in our calculation? We haven't done anything with temperature, right? The previous problem said at a constant temperature. This one gives a specific temperature. You'll often see a specific temperature given because the temperature affects the rate constant. So they're just saying this is all happening at this temperature. We're like, cool. We don't need to use it, okay? So we don't need to use necessarily all the numbers that are given in a problem, right? Like that one with the density on the review worksheet. And you're like, how am I supposed to incorporate the density? Why'd they give me the density? To mess with you. That's why we gave you the density. Okay. If the initial cyclopropane concentration is this, okay, so that's useful. That is equal to A at time 0. And again, I'm just calling it A because it's easier to write than cyclopropane or the formula for cyclopropane. What will the cyclopropane concentration be after 235 minutes? So 235 minutes is the time. And this guy over here is my rate constant, yeah? Well, let's write out the integrated rate law for a first order reaction. I think it's always good to write out the equation before you start substituting numbers in. Because once you start putting numbers in there, then things like minus signs and stuff can get confusing. So we're trying to find A at time t. We have the rate constant, we have the time, and we have the initial concentration. So we can plug all these numbers in. So -1 times the rate constant, 3.36 times 10 to the minus 5 s to the minus 1. And then we need to multiply that by the time. Can we use minutes? No, it has to be seconds. And this unit here will help us remember that. So t is equal to 235.0 minutes. We need to convert that to seconds. 60 seconds in 1 minute. And so this equals 141.00 seconds. This had 4 sig figs. Might be a good idea to just remind ourselves of that. Not a big deal. Okay, so that's our time in seconds. We're going to put that in here. 141.00 seconds. and the seconds are going to cancel out. And then we're going to add the natural log of the concentration at time 0, 0.0445 molar. And I kind of ran into myself. Let's separate that out a little bit. So now we can calculate this. We can find out, let's finish this off here. The natural log of A at time t is equal to, I'm going to do some math, negative 3.36. I'm assuming you all know how to use the scientific notation button on your calculator. It just really makes life so much easier if you do that instead of one of the other ways that you can get the same results. Negative 3.5860. Again, I've got some things with 3 sig figs. We'll find out that a lot of our calculations are going to end up with 3 sig figs. But again, write down a couple extras. So then what do we do to get natural log of, what do we do to get the actual concentration? E to the both sides. So e to the negative 3.5860. 0.027708, that's probably enough. And 0.0277 molar. Is that a reasonable concentration? Is it a possible concentration? We started at 0.04, and after some time, we're at 0.02. It's gone down. That's encouraging. Doesn't prove that we did it right. If it went up, we got something backwards. If we get a negative concentration, something's really wrong. Any questions? And I got the answer right again. Nice. Okay, second order rate law. So here we're still looking at a simple decomposition, but for second order. So the rate is equal to K times the concentration squared. The rate can still be defined in terms of the change in concentration of A over the change in time. So we're going to take those two and set them equal to each other, which gives us the differential rate law. And then we go, woo, calculus, and we get this.
Is it on the same button as pi?
Which one?
Is it this one?
No. It's this one. This one.
Oh.
Yeah. So your calculator should have natural log and base 10 log, and the anti-log for base 10 is 10 to the x, and for natural log it's e to the x. On this calculator, those are on the same button, natural log and base 10 log. And so when you push it the first time, push that button once, it'll give you natural log. If you want base 10 log, you just push the button again, and it'll give you the next one. Great question. Okay, so this is also in the form of a line. Y equals mx plus b. So here, the slope is directly equal to the rate constant. And y is going to be 1 over the concentration at a given time. And that intercept is going to be 1 over the original concentration. You get a linear graph when we plot 1 over concentration versus time. So consider the equation for the decomposition of NO2. The concentration is monitored at a fixed temperature, So they didn't bother telling us what it is because we don't need to know. Measured as a function of time, and the data is tabulated. So here's the data. Wow, look at all those numbers. Show by graphical analysis that the reaction is not first order and that it is second order, and then determine the rate constant. So if you were doing this with just a calculator, this would be a very tedious problem. When you're doing this on Excel, the hardest thing is just typing in the data and then doing multiple calculations on the data is a piece of cake. And we'll see how that works in lab. So we can tell by making graphs whether it's first or second order. So this is a first order graph, natural log of A versus time. So we graph that, and you may say, well, that kind of looks like a line, right? Well, look at the R squared value. It's not given here, but it wouldn't be very good. The other telling thing is that it's above at the start and the end, and it's below in the middle. This is a curve, not a line. It's just, in an aspect ratio that looks like they're kind of close. Here we have 1 over concentration versus time, and we get a nice straight line. So this straight line tells us that this is a second order reaction. I will not be making you graph things on an exam, but I might give you graphs like this and say, what's the order of the reaction? And based on what is being graphed, you should be able to tell me first or second order. So use the graph and best fitting line to predict the concentration at 2,000 seconds. Again, it doesn't go to 2,000 seconds. We can't read it off the graph, so we need to use the equation. We have the equation for the line here, and the computer's going to use y and x. We need to remind ourselves, what are we graphing again? 1 over a at time t is equal to kt plus 1 over a at time 0. This is the rest of the equation, so we can just copy that down, not worrying about 1 overing or anything. Instead of x, we're using t for time. Bless you. So our slope, 0.255. What are the units? Second order. Second order reaction, rate is equal to rate constant times a squared. The rate has units as molarity per second, and molarity squared is the other unit. So we have molarity per second divided by molarity squared, which is the same as molarity over molarity squared times seconds, and we get molarity to the -1, seconds to the -1. Not a big deal, but just want to remind you how you can find that. So the units here, m to the -1, s to the -1. We're going to take that and we're going to multiply it by the time, which they gave us in seconds, and then add 100. So we'll do the calculation. 0.255 times 2,000 plus 100. 610. So what's happening with the units? Well, this is the y-intercept. It's going to have units that y has. Y is 1 over a concentration. This has units of m to the negative 1. These seconds will cancel out. And so this answer here has units of m to the minus 1. Again, if you don't follow that, that's fine. I just want to show you that the units are working out. So the calculator's giving me 610, which, technically you'd say maybe has 2 sig figs. We're going to go with this number with 3, and we're probably going to report our answer to 3 sig figs. So we're just going to leave it there, and it's fine. It's fine. So that's 1 over A. How do we find A? Well, we could multiply both sides by AT and then divide both sides by 610. Or we could raise both sides to the negative 1 power, or we could upside down the whole thing. Because this is equal to 610 over 1. And so if I just upside down it, I get A T is equal to 1 over 600. Ugh. So 1 divided by that. Oops, not there. 0.0016393. Then because we inverted molarity to the negative 1, now we've got molarity again. And so we should probably report this as 0.00164 molar.
Professor?
Mm-hmm.
I got 0.255 times 2000 plus 100. I did not get the same answer.
You didn't get the same answer? Okay, let me check.
Even
What?
the final answer is correct.
0.255 times 2000 plus 100. I'm getting 610. Yeah.
Why would it not be 1 or 1 over 100?
That's a good question. Why not 1 over 100? Because this is 1 over 100. This is the value of B, which is equal to 1 over the initial concentration. But 100 is not the initial concentration. It's 1 over the initial concentration. And that's kind of that same thing we were talking about with the first example, right? We need to kind of get that straight in our minds because it's easy to think that. Any other questions? Still not doing it? You're doing 0.225. It's 255. There's something about 0.255 or 255. I don't know. A lot of students write down 225. Yeah.
And then the negative 1 power goes away, or?
Yes, because negative 1 power means 1 over that.
So
So-
if you write it in the fraction, you just don't put the negative 1? Like how you wrote 1 over 6 and you don't have to put the 1 here?
So the negative 1 here needs to be there if I keep it in the denominator. But if I just write it in, not in part of the fraction, it would go away. Yeah, because what I've got going on there is I have 1 over m to the minus 1,
Oh, okay,
which equals 1 over m, right? So that is m. And that's another thing that'll kind of come up. And I'm not going to try to trick you with units, but that is a piece of math that kind of shows up over and over again. Great questions. Any more? Okay. It wasn't until a little bit later that I started screwing everything up. But this lecture is going to be much better because I reminded myself what I was doing. These sorts of things happen when it's been a year and a half since you got to teach the class. Okay, Zero order integrated rate law, doing the same thing. Here's the rate law. Here is the definition of the rate. Set them equal to each other. Integrate them. This is what you get. Again, it's in the form of a line. They did that on purpose. Y equals mx plus b. So here, the slope is equal to negative k. So whatever we get for our slope, multiply it by -1 to get the rate constant. Is that somebody knocking on the door? No?
The door's unlocked.
Yeah, it is, but sometimes, I don't know. No, just my imagination. I do that sometimes. Okay, so let's do, oh, actually, we're not going to do a problem with that one. I think because we did two other ones, this is just along the same lines, slightly different equation. We don't need to do it in lecture. Okay, so now we're going to talk about half-life. And this is the same half-life that you learned about in Chem 3A long, long time ago, right? It was before 1A, and 1A seems like it was a long time ago. For some of you, it actually was a long time ago. Half-life is how much time for the concentration of the reactant to fall to 1/2 of its initial value. So if we have an initial concentration of 0.5 and the half-life is 50 seconds, what's the concentration after 50 seconds? You divide by 2, so 0.25. So 1 half-life, we're going to divide by 2. So 0.5 molar dividing by 2, cutting it in half, right? So 0.25 molar. This is after 1 T1 half. What happens in the next 50 seconds? It gets cut in half again. So 0.25 molar divided by 2 equals 0.125 molar. So this is our concentration after 2 half-lives. It doesn't work to say, well, the first half reacted in 50 seconds and the second half reacts in another 50 seconds. It's not linear like that. The half-life expression is going to depend on the order of the reaction. When we're talking about radioactivity, everything is first order, and so that's what people are more familiar with. We're going to look at zero order and second order as well. So how do we get the equations for half-life? We start with the integrated rate law. This is just a rearranged form. It was on this slide when we first talked about it. We just kind of ignored it. It's in this form just to make it easier to rearrange. So we take our integrated rate law, and we recognize that when T is equal to T1 half, then the concentration at that time is going to be equal to half the original concentration. So we're going to substitute this in for AT. You will not be required to derive these things. I just want you to see how it works. So that gives us 1/2 A0 divided by A0. And that's going to equal -K times T1 half. We're trying to get an equation that says T1 half equals something. Well, A0 over A0 cancels out, right? So now we've got the natural log of 1/2 is equal to -K times T1 half. So natural log of 1/2 is negative 0.693. We usually use 3 sig figs on that. That equals negative k times t 1/2. And so if we divide both sides by negative k, the negatives cancel out. T 1/2 is equal to 0.693 over k, the rate constant. Any questions? This equation is given on that list of equations also. Again, it's not labeled, but it's there. And you do not need to know how to derive it. I'm deriving some of these things because I think it's helpful for you to see where these equations came from. We didn't make them up, right? We found relationships and we used math to help us understand them. And then we can use all that stuff that they taught you in math class. You're like, why do we have to do this? Well, because someday you might be a scientist and you might need to do this, or at least understand how someone else did it. So that's our equation.
Can you show me that later?
I can show you that later. Yeah, absolutely. Let's see. Okay, so for the first order reaction, half-life is equal to 0.693 divided by the rate constant. The half-life doesn't depend on the initial concentration. Doesn't matter how much there was to start with, it just gets cut in half each time. And so that means that the half-life is the same throughout the whole reaction. That is actually unique to first-order reactions. First-order reactions are the only ones that do that. Zero order and second order, all other orders, the half-life changes as the reaction goes on. So this is what is used for radioactive things because they are first-order reactions. And when we get to chapter 21, near the end of the semester, we'll come back to this guy because we're going to talk about radioactivity. Any questions? So someone nicely pointed out yesterday, your handout is black and white. And so you can't see which ones are the red dots. So this is an example of something that's not completely accessible, right? Someone with color issues would have trouble with this. So what they should have done is made them red triangles. So on your paper, circle or box or color something, make those look different so that you can see what's going on there. So these images are depicting a first order reaction where A goes to B at different times. The black circles are A, the red circles are B, or whatever you made them into. And they're asking, what's the half-life of the reaction? So we started with how many black circles? 10. There's 10 black circles. What would be true at the half-life? It'd be half of 10, 5, right? So we need to find the box here that has 5 black circles. So that's this one right here, right? They're scattered around, so they're a little hard to count, but 1, 2, 3, 4, 5. So the half-life must be 90 seconds. Any questions? A first-order reaction has a half-life of 25 minutes. If the initial concentration of A is 0.3, what's the concentration of B after 50 minutes? So this was where I made my first mistake in lecture yesterday. And it says, don't use a calculator. I like my calculator. It's okay. Well, we have an initial concentration of 0.3 molar and the half-life is 25 minutes. So after one half-life, it gets cut in half. So that's after 25 minutes. What's going to happen in the next 25 minutes? It's going to get cut in half again. 0.150 divided by 2, and that is going to be 0.075, and that's after 50 minutes, which is 2 half-lives.
That's one of them.
That's none of them. Yeah. So, what did we do wrong? Does anybody see it? It took me a minute. It's first order, so we're doing that part correctly. We did our thinking and our math here correctly. We overlooked a little detail in the question. What's it asking for? After 50 minutes, the concentration of B. We found the concentration of A. So this is 1-to-1. B would have started at 0. For every A that reacts, you get a B. So this is the amount of A that's left. How much of it reacted? We'll take the initial concentration and subtract what we've got left. And you might say, not fair, I want my calculator. Yeah, I do too, but it's 0.225 molar. Even if you're like, no, I'm not doing that math in my head, you could still pick out the correct answer from the multiple choice, right? That's the initial concentration. That's not right. 0.15 is not right, and 0.1 isn't right, so it must be the other one. Any questions? This kind of thing is something you do need to look out for. We're going to do that to you in this class, me and the homework. First order reaction has a half-life of 26.4 seconds. How long does it take for the concentration of the reactant in the reaction to fall to 1/8 of its initial value? There's 2 ways to do this problem. 1/8 is a nice number, right? So we start with 1, and after 1 half-life, we get 1/2 of it. And after 2 half-lives, we have 1/4. And after 3 half-lives, we have 1/8. So we can think it out and say, well, this is 3 half-lives. 3 times 26.4 seconds. It'll take 79.2 seconds for it to fall to 1/8 of its initial value. What if it was like 1/17 or 29% or something ugly like that? Then we'd have to do the math. So how would we do that? Well, we have our first order reaction integrated rate law. And the rearranged form is actually more useful here. So we know that A at time t is 1/8 of that. So I'm feeling lazy, so I'm just going to change it in here. 1/8 of A0. And then the A0s drop out. Natural log of 1/8 is equal to negative K times the temperature we're looking for. Uh-oh. We don't know what K is. They didn't give it to us.
They gave you the time instead.
They gave us the half-life, and there's an equation that relates the half-life to the rate constant. Because for first-order reactions, the half-life doesn't change. So we can use this guy to calculate K. So let's rearrange that. Then K is equal to 0.693 divided by the half-life. 0.693 divided by 26.4 seconds. Zero point 0.02625. So now that we found that, we can put that in here. We need to solve for t. Some of you can look at this and do it on your calculator while you're rearranging it, kind of in your head. That's great. You do not need to show me all your steps. For those of you that can't do that, don't even rearrange anything. Use the number solver on your calculator. So how would that look? Pull up the number solver and just do clear, move the cursor and clear to get our two boxes, right? So on the left-hand side, we have the natural log of 1/8. Natural log of 1 divided by 8, and we'll close the parentheses there. Then on the other side, we have negative 1 times 0.02625 times our variable. It doesn't give us t, we can use x. Press enter, start x at 0, press enter 2 more times. Where am I? T is equal to 79.2 seconds. Ta-da!
That seemed like a whole lot more work.
This way than that way? Absolutely. Yeah, it absolutely is. I didn't even write all this out for the lecture yesterday. This is much easier, so do that if you can. The thing is, you can't always do that. Like, 1/17, you can't do it.
Don't underestimate my ability.
Well, I would have a really, really hard time doing that. It can probably be done, but I don't know how.
Just because you told me I can't.
Questions? Anybody have any questions?
Would you rather have a dog that can talk or a cat that'll pay half the rent?
I didn't mean questions like that. But I'd rather have the cat that can pay half the rent. Because my kids used to watch Dexter's Laboratory, and he once did something and made his dog be able to talk. And the dog said, ball, ball, Where's my ball? Do you have a ball? Is that food? Can I have some? Ball? I would not want to live with a talking dog. No, thank you. Okay, chemistry. Here's the second order integrated rate law. We can do the same thing to find the half-life equation. So for AT, I'm going to sub in 1/2 of A0. And I'm going to go through this a little quickly because,
We're running out of time.
well, I mean, we're low on time. The other thing is, the people who like this sort of thing don't need me to go slow. And the people who don't like this kind of thing, this will just be over faster. So there's my reasoning. How's that? So I need to get t by itself. Oh, this would be t 1/2. So I'm going to subtract 1 over A0 from both sides. And that equals k t 1/2. In order to be able to subtract these things, I need to have the same denominator. If I multiply the numerator and the denominator by 2, I can change this into a 1. Those 2's cancel out. And then I have a 2 up here. So what I really have is 2 over A0 minus 1 over A0. So that comes out equaling 1 over A0. If you didn't follow that, don't worry about it. And then we want t 1/2. So t 1/2 is 1 over k times A0. T 1/2 is 1 over k times A0. Yeah. Yeah, feel free to write that down and puzzle through it later. Remember, I'm posting these lectures on YouTube and linking them on Canvas, so you can go and catch them there if you need to see that again. Okay, so for a zero order reaction, we have the half-life also depending on the initial concentration. But here, the half-life gets smaller, gets shorter as the concentration decreases. The half-life gets shorter as the reaction proceeds. For the second order, t 1/2 was 0. No, not that one. Shoot, I made the same stupid mistake again. You see what I did? I did not come up with that answer. I'm going to run through this again. Sorry. Oh, wait a minute. Okay. Brain fart. Losing confidence in myself. I did this one correctly. And the next one, we don't have a slide for deriving it, so I didn't derive it, so I didn't do it wrong. Phew! What I did forget to talk about was, in the second order, the half-life gets longer as the reaction proceeds. Because here we have our initial concentration. The half-life depends on the concentration. So later on in the reaction, this number is smaller. If I'm dividing by a smaller number, t 1/2 changes. So that gets longer. That's the deriving slide that I just said wasn't there. Okay. Let's do this one. Oops. This is A0. So I'm going to add KT to both sides and subtract 1/2 A0 just to get rid of that negative sign. So this is equal to 1/2 A0. So KT equals A0 over 2. So T1/2 equals A0 over 2 times K. Again, it's good to see how that's derived. You do not need to know how to do that. I'll never ask you to do that. Here, because the concentration is in the numerator, as the concentration gets smaller, the half-life gets smaller. So the half-life gets shorter as the reaction proceeds. So this is a very useful table from the textbook. So you might want to go onto the slides that are on Canvas, pull up this slide and take a screenshot of it, and you can have it on your phone in your photo library to look at whenever you need, except on an exam. This just summarizes all the stuff we've talked about. So we have the order, we have the rate law, we have units for the rate constant, we have the integrated rate law, we have an illustration of the straight line plot, and we have the half-life expression. I'll give you this and this and this on that useful information. And I also give you, the expression for the half-life. And I put them in the chart in order, they're from left to right, 0, 1, 2, but I don't identify them. We should be able to figure out what to graph for a straight line by looking at the integrated rate law and saying, okay, well, that's y equals mx plus b. What's y? What's x? What do I graph? Okay. These guys you should figure out because they're so close to just the definition of what the order is, right? A rate law says the rate is equal to a rate constant times the concentration raised to a power. That power is the order. The units of K, if you need those, you can figure them out by plugging units into this rate law. These guys, kind of hard to remember, so I'm giving those to you. Any questions?
Would you rather have?
No. Any questions related to the lecture topic? I'm not even going to say chemistry questions because, okay. A decomposition reaction with a rate that is observed to slow down as the reaction proceeds has a half-life that depends on the initial concentration of the reactant. Which statement is most likely true? A plot of the natural log of concentration of the reactant as a function of time is linear. What order is that true of? That's true of a first order reaction, right? So if that's true, then it's first order. The half-life increases as the initial concentration increases. Which one is that true of? We forgot already. Which one of these would T1 get bigger if A got bigger? It's this 0, 1, right? So this is describing a 0 order. A doubling of the initial concentration of reactant results in a quadrupling. What is that statement true of? Second order. Well, does a first order reaction, does a 0 order reaction slow down as it goes on? No, because the rate is just equal to the rate constant. It doesn't depend on the concentration. So it says the rate is slowing down. That tells us it's not 0 order. It says the half-life depends on the concentration. For first order, does the half-life depend on the concentration? No, it doesn't. But, if we don't remember, we go look. That's 0. We decide it wasn't this one. Here is the half-life for first order. Concentration doesn't come into it. So it can't be first order. Therefore, it's second order. That kind of question could show up on an exam. Just letting you know.